And yeah, it's my pleasure to introduce the team today. Dr. Curtis Atkinson joined the eScience Institute in February of 2024. He received his PhD in evolutionary anthropology from UC Davis with an emphasis in computational social science. His postdoctoral work involved analyzing open source software communities and how they persist, as well as expanding his tools to include machine learning and other AI approaches to understanding text. For example, GPT is a zero-shot translator and other applications for sure. With us, we had in the past and today as well, Jihyeon Bae, who's a PhD candidate in the political science department at the University of Washington. She's also passionate about applying NLP models in her work. Born and raised in South Korea, she received her BA in International Studies from Taeyong University in 2019, with additional training in the Applied Mathematics department. With us is also Daniel Vogler, currently pursuing a master's degree in data science at the University of Washington. Before graduate school, he worked as a management consultant, primarily supporting clients in healthcare and retail. Daniel graduated with a BA from Princeton University in 2021. And they're here today to kind of take a closer look at the data science workflows that were used in the water use project over the summer in our DSSG program. And the title of their talk is Serving Client-Side Computation on a Static Server, WebAssembly. Thank you so much and welcome, Curtis and water use team.
Hey, everyone. Hey, hopefully if I don't hang out right here, the people on Zoom will still be able to hear me, because I've noticed the room is oddly weighted that direction. So I can guarantee you that I'm just gonna like start drifting over here to talk to most of you. So hopefully that works for anyone who happens to be on Zoom. So yeah, I'm Curtis Atkisson. Believe it or not, I didn't provide any of that introduction to Nicoletta. It's always fun to hear what people distill to introduce you. But yeah, I'm a data scientist at eScience Institute, specializing in computational social science and studying the community dynamics of open source software and open source software developers. So if you need any help with data science stuff, if you're interested in computational social science, if you want to do open source software development and you don't know how to get started, all of that stuff, please come talk to me. My email address is very easy to remember. It's catkiss, like you're kissing a cat, at uw.edu. And we also recently started some R-specific office hours amongst other topics at the eScience Institute. So if you have any topical questions about R or Python, machine learning, or high performance computing, please find those topical hours and come to them. So today we're going to be talking about a relatively new tool. I was reminded today that 7 years is a pretty long time in terms of an internet tool, but still relatively new tool that you could add to your toolbox as an engineer, an analyst, or a scientist. So we won't be talking about a new research result or any sort of cool statistical method. I know you hear those sometimes, but rather a type of programming and a way of presenting results that could add a lot of flexibility to how you accomplish your goals and present your deliverables to whoever that might be. So I think it's really cool, and I hope you all can jump on the train as well. Now, you probably remember Jihyeon and Daniel from a couple weeks ago. Like Nicoletta said, Jihyeon is a PhD candidate in poli-sci, and Daniel is in the last year in the Master's in Data Science program. So I know that Jihyeon and Daniel think the tool we're talking about today is frustrating because it had a little bit of a learning curve. but hopefully they've also come around to how cool it is. So to start us off, I'd like to motivate this tool with a few user stories. So who here is familiar with the idea of user stories? A few, okay, a few. Who has used them to help design design something in the past? Yeah, cool. So just for everyone else, so user stories are concrete examples that allow us to describe actual use cases of the thing that we're designing, and then use those to design our solutions in a robust way. And they can also help with issues like technology review, which is when we decide the approach that we're going to take to a certain problem. So let's talk about some interesting people. If my next button would work. Okay. So Sarah is a data scientist for an affordable housing nonprofit. They want to be able to show an analysis to a wide audience and allow that audience to explore the data. Their organization doesn't have money to host an application on a server. Plus, they've never really designed or developed an app before and don't really know what that would look like. Okay, cool, Sarah. Like, way to step outside of your comfort zone. Get after it. So who's next? Jasmine. Jasmine is a recent master's in data science graduate. They learned how to do certain things in different languages, like machine learning in Python and graphs in R. And they would like to be able to use all of those languages as they work on solving a new problem. And they are excited to learn a new skill to add to their toolkit. Dang, Jasmine, you're really killing it. Way to stick with it. Who's next? Dan. Dan is a journalist that uses a lot of data-based results. They want to be able to access those results even years into the future. And they're worried that some of the organizations that produce those results may not be around when they need to access them in the future. They know that they can save a web page to their computer and then open it somehow, but not much more than that. And finally, Julio is an analyst for a financial firm. They want their new trading insights app to be available to their traders on any machine that they happen to log on to. But they cannot guarantee the capabilities or the architecture of the machine that the traders might use. But this tech needs some pretty sophisticated stuff. They're willing to invest considerable effort to develop a high quality app. So those are 4 user stories that seem pretty diverse. And let's look at each of these in a little more detail with what their desires and their limitations are. So here we have Sarah. Sarah wants a dynamic application, something anyone can interact with that uses technology that they know. But Sarah can't pay to host that application on the internet. And she doesn't really have a whole bunch of time to add some new skills into her tool set. What about Jasmine? So Jasmine has like all of these skills. Like they learned a bunch of stuff and they want to be able to tie all of those together and use different languages when it's most appropriate. And they're also happy to learn a new skill. But what they know is that some of these languages don't really play well together. You might have, for instance, a typed language that you're trying to use with a scripting language, and that could be an issue. Dan. So Dan has all of these resources that they don't want to disappear. And they also want to be able to know what version they got their conclusion from. So they want to make a conclusion 3 years ago and then synthesize it in this big piece they're writing right now. And they want to be able to say exactly which version of the data they're using to make this claim. And then they want to be able to access that whenever. But Dan doesn't really have all that much technical knowledge. And then finally, Julio, who is both very well-resourced and very skilled, wants to be able to give users access to this app no matter what machine they happen to be on. But Julio knows that technical programs require some pretty specific architecture sometimes. So this might seem like a too diverse set of user stories. Like, how could one piece of technology really help us deal with all of the problems that we've described here? But there is this relatively new technology, it's just now maturing, that can actually address all of these concerns at the same time. And it goes by the name of WebAssembly. So WebAssembly, or WASM, which is what the cool kids call WebAssembly, is a binary instruction format that has a corresponding code format that allows compact binary code to be interpreted by modern programs like web browsers. Holy crap, that was word salad. What does all of that mean? What it means is that the code that's being executed is binary. So it's very low level on the machine. And this gives us really good performance, so highly performant code. The corresponding text format means that if we can get something into that binary code, then it can be run by the computer. And this allows us to use many different languages as long as someone has compiled or transpiled that language into WASM. So while these things are great for the developer, the scientist, or the analyst, one of the primary benefits of WASM is that it allows for the delivery of highly specialized code for client-side execution from a static server. So why do we care about being able to run highly specialized code for client-side execution from a static server? Well, first of all, when websites primarily serve up computation done on a server, the processing power of the user's machine is simply being used to render the results of those calculations. But that leaves all of that personal computing power completely untouched and unused. I have like 1,000 supercomputers worth of processing power in my computer. I mean, not today's supercomputers, but back in the day. So IBM estimates that there are over 200 billion CPUs currently running. So most of those aren't personal computing power. We don't have access to them. They're government, or a lot of them are used for defense or things like that. But many of them are available. And we want to be able to leverage this spare silicon that's just sitting around. Now, using it to do things is not a novel idea. So there's this old effort called SETI. Has anyone ever heard of SETI before? The search for extraterrestrial intelligence. So the search for extraterrestrial intelligence is a distributed computing platform that allows people to devote cycles from their own personal computer to search electromagnetic signals for signs of extraterrestrial life. So you could say like, hey, when my computer's sitting around doing nothing, you can use it. And then that would help us learn if there was extraterrestrial life. And the recent Nobel Prize in chemistry, did everyone follow the big AI large language model use in chemistry? So that prize went to people studying protein folding. But that protein folding work was actually building off of work originally done on a distributed system like I just described for SETI, that used personal computing cycles to understand how proteins fold from a given amino acid sequence. And there is so much silicon that's sitting around that could be put to good use. And when we are using other people's silicon to do computation, not only can we get more done in the world, but that also allows us to keep costs low. So serving a static web page is cheap, like dirt cheap. Even in some cases, dirt cheap equals free. So GitHub provides GitHub pages for every repository for free. And that's a great, amazing resource that they give us. But those pages are static. And what this has meant historically is that we can't use this free resource to deliver dynamic computation. We can't let the user click around and do different things We can only serve them static websites. But what we can do is we can use this website to statically deliver instructions to run a program that is then executed on the user's machine, which is what WebAssembly allows us to do. In addition to being cheap, serving static web pages is also much easier than serving dynamic web pages. And this makes such web pages robust to high load. So if you had a sudden rush on some result that you presented or some app that you made, and the web page was threatening to collapse under the load, then it will be less likely to happen if you're not serving that dynamic computation, and instead you're just serving a static source. So in addition to those two high-level reasons to use WebAssembly, since WASM is an instruction format and not a language, there's actually no new language to learn. You don't have to learn a language called WebAssembly. WebAssembly uses whatever language you have at hand, and very importantly, ties it together with JavaScript. So JavaScript, which is the primary driver of all work on the front end of web development these days, is what we use to interface with this instruction format. So it's definitely a pro. We don't have to learn a new language. But what it means is that someone has to have done the work to make the language work with that instruction format. So they need to have compiled it into WebAssembly so that you could use it. And not just the language, but also libraries or packages that you want to use have to have been compiled into WebAssembly. And once they are, though, once that work has been done, and it has been done for over 40 languages, that includes basically any language you might want to use. Esoteric languages you don't even know you want to use, like Julia or MATLAB, you can run those in WebAssembly. But once that has been compiled into WebAssembly, those functions, the ones that you're used to using, the pandas function that is just like the thing you use every other day, the dplyr method of tidying data in R that you're used to using and you want to use, once those have been compiled into WebAssembly, they can just be exposed as new JavaScript functions. And that allows anyone who knows JavaScript, or even some people who are just learning JavaScript, to be able to work with them in a JavaScript native way. So this all, I hope that this all sounds very cool. In the tech community, WebAssembly has inspired some pretty dramatic statements. So one of these quotes is that WebAssembly allows us to maintain the versionless, feature-tested, and backwards compatible nature of the web. So this is a quote from the organization that sponsors WebAssembly. Modern application development and research takes place in an iterative way, with a goal of regularly adding small improvements to what we already have. So this gets rid of the need for hard versions of applications and instead allows for continuous updates to each application. Google was famously in beta for like, what, 25 years or something like that. So they didn't need versions at all. And by uniting the computation and the presentation parts of the web app into one framework, WASM facilitates well-tested versionless applications that maintain backwards compatibility. So in effect, this means that any application that is built using this framework won't be disappeared. Like, it's not just going to go away. Anyone can have the resources and can run that program on their computer itself. And then all of those iterative changes will work consistently as the application changes over time. So Solomon Hykes is one of the co-founders of Docker. Who knows Docker? Knows Docker? Docker is a really important tool in data science these days. It's a containerization technology. So containers are great because they allow us to deliver a consistent computing environment across many architectures. And indeed, actually, my original interest in WASM arose because I wanted to do the water reuse project as a Docker container. But my friend advised me that Docker is actually not as portable as you think it is. Not as many people as you want to be able to use it will be able to use it, and you're not going to get as consistent of an environment as you want. So in 2016, 8 years after Docker had started working, Solomon Hykes said, if WASM existed in 2008, we wouldn't have needed to create Docker. That's how important it is. WebAssembly on the server is the future of computing. So 85% of you know what Docker is. And one of the creators of Docker is saying, well, actually, like, we don't need our technology anymore. We have this better, more complete technology that we can use. So WASM ensures that we have a consistent environment because what we're working in is the walled garden of the browser. So we've essentially taken the environment constructed by the browser and we say, hey, that's what we get. That's what we're allowed to use. And then we can operate within that. And all of these browsers have been optimized across all of these architectures. So they've enforced a consistent environment because of their desire to work across many different architectures. So being in this walled garden of the browser provides other benefits, which we'll talk about in a bit, and also some difficulties, which we will discuss later as well. And finally, Ben Teitzer, who is a researcher at Carnegie Mellon University, describes a number of benefits of WASM. Ben says WebAssembly holds promise as the elusive universal code format with strong security properties, broad language support, and excellent performance. So Ben believes that WebAssembly offers us the ability to tie together many different languages in a universal format that is secure and performs well. So WASM, as I said, is a technology that is now maturing. So WebAssembly was released from preview in a beta stage in March of 2017, so a little over 7 years ago now. And since then, it has become an official project of the Worldwide Consortium, which is the group that the World Wide Web Consortium, also called 3WC, which is the group that tries to standardize and steward the internet. And WASM has had continuing adoption. And as of June 2019, when Chrome finally added support, all major browsers support WebAssembly. And not only that, but the last estimates showed that 99% of all browser requests support WebAssembly. So this means if you develop something in this framework, you're going to have really good adoption. Almost everyone's going to be able to access it. And indeed, I think that's actually better than some of the more esoteric JavaScript frameworks. But as it has gained adoption, people have begun developing WebAssembly 2.0, which very importantly will include 64-bit support, which we'll talk about that being an issue a bit later. So that will make WebAssembly even more powerful. So now I want to show you some things that might look very normal to you, like not surprising at all, but are actually super cool. So the first one is called pyodide. So pyodide, how do I make this go away? So this is pyodide. What do people notice about pyodide? What does it look like? What? Command line, and not only command line, it looks like your command line after you type what command into it. Python. This is just Python. This is just Python running in the web browser. Nothing there. This is not accessing the Python that is on my computer. This is just delivered. Anyone, you could take a Chromebook. If you have a little tablet with you here right now. You could go to the pyodide.org and go to their repo, and you could get Python on your Chromebook right now. So we could do whatever sort of typical things that we might want to do in Python. I don't code that often in Python, but I assume no, square root is not. Well, we could use it as a calculator, right? We can do all of these things. What is 2 to the 236th? That's not right. Oh, jeez. Those live demos, don't do them. There we go. There's 2 to the 236th power. Okay, so that's just like bog standard Python, and so it's not actually that cool, except it's just in your browser. Like nothing else is happening. I didn't have to install a single thing to just make Python work like this. All right, so another cool thing that looks very normal, we have R. This is the R GUI. If you just install R and you pull up the R GUI, this is what you get. And we're running R 4.4.1, which is the most recent version, I think. Yeah, there might be a 2. And we can just make our stuff happen. So let's say I want to use the library dplyr, which is a very popular library in R, and I hit enter. So what it tells me is you haven't actually installed dplyr, but I got you. You can install dplyr. Would you like to install it and run it in this display on your browser? So I say yes, and it just takes a minute, a relatively short minute to install dplyr. And now I have access to dplyr and everything that I might want from it. So I can, let's see, I can make a subset of the iris data set and just select only those variables that start with petal. So what's that look like? So now here we have this data set that is 2 columns and just the petal columns. And I can come up here and I can say, I want to take a histogram of only the petal widths. And here I now have this histogram just as I would have if I were using R natively. And I didn't have to install a damn thing. And it took like 2 seconds once I pulled it up to get it working. So you could go to anyone's computer and you could say, hey, I want to show you this thing I made. And maybe they don't use R and you wrote it in R and you get there and they're like, I don't have R, and you're not going to install it. So you just go to the Weber REPL, R-E-P-L, and you could just run whatever code you have immediately. Okay, so it seems very normal, as we might expect, but I think it's very cool. And indeed, I know that pyodide is, there was recently a big set of legislation passed in the French legislature that required data science to be taught starting in grade 6 or grade 7, I think. And pyodide is one of the key pieces of how they're delivering that to people who have a wide variety of machines and maybe not consistent access to the same machine. So those are really cool things. And now we're going to have Jihyeon, who's going to describe an example application, what problem it solves, and why WebAssembly would be a good choice for it.
So now that we have a better idea of what WebAssembly is and how cool it is, I want to bring your attention back to the user cases that Curtis introduced to us earlier. So remember Sarah's case. Sarah had a problem of not having enough resources meaning skill sets and also the money to spin up a server. And I'm going to talk about how WebAssembly can resolve those problems given many of the characteristics that it has. So not having resources in terms of money and skill set isn't a unique problem for Sarah, but it's a common challenge faced by lots of non-governmental organizations. So WebAssembly can mitigate this problem in two ways. First, WebAssembly is serverless. So this really meant that there's no need for designated remote server to handle requests and run the computations. But instead, all they need is a set of files including, something that ends like housing underbar final.html and another JavaScript. And with that set of files, all of these computations will take place in the user's browser. The core R functions or Python functions will take place in the user's browsers like Safari or Google Chrome without relying on a remote server. So WebAssembly is also static. To be concrete, static web pages do not require a databases or any other external logics that gets updated based on the user's input. So it's much easier to maintain the website in the long run. Also, as a bonus, there are already a lot of platforms like GitHub Pages that will host static web pages without any additional costs. Another characteristic about WebAssembly is that it doesn't host any web page, but a good one where users can interact with features of the website, meaning that it's user interactive. So what this really means is that whoever clicks on Sarah's web page, either by accessing the GitHub page or by getting a zipped folder that contains all these building blocks for the website, will be able to actively drag and drop the data sets, adjust the parameters if they're running statistical analysis, and immediately see the results and even visualize them with their own customizations. So the user does not even have to install R, doing all of these things like downloading the data set or changing the visualizations. In the case that you might recall from several weeks ago, we created a website visualizing the water reuse potential, right? So the user could click on the web page on the GitHub pages, and they could easily recalculate the index based on the PCA, and they could easily download the recalculated data sets as well as visualizing it on the map. So all of those customizations, depending on the user's purposes, can be achieved by hosting a website on using WebAssembly. And WebAssembly makes all of these features possible thanks to its characteristic of being client-side computation. So when the user provides input data, either by giving the numbers into the calculator or selecting a subset of data sets that they want to average out, the WebAssembly module will take over. So the WebAssembly being the instruction triggers the functions, performing real-time calculations and generating whatever the output should look like. And Curtis mentioned the WebAssembly being a binary instruction at the end of the day. Being the instruction in a binary format means that it's formatted to be a low-level calculation, and it also allows all of these browser-based calculation to run fast. To take another quick example from Jasmine, in their case, the main challenge was having multiple languages work well together and weave all of them through seamlessly. For example, Jasmine might wanted to use the output from Python functions to be fed back into the R function. And all of those switches between different native languages should have been smooth. Now, WebAssembly is language agnostic, meaning that it doesn't discriminate which language is performing the actual functions, because it's a simple instruction format rather than a language. Now, regardless of which functional languages that computations rely on, WebAssembly will channel the native task to the browser as long as there are nice compiling or translating tools from native to the binary instruction format that WebAssembly can digest. And fortunately, there are a lot of libraries for this specific step. For R, we have WebR, and for Python, we have Pyodide. And given all these tools, the translations between native languages in a format that WebAssembly can take in is pretty easy.
So one of the, does anyone remember Java applets? Java applets, yes, yes. What was the not homebrew? Anyway, so Java applets were these little things, these little programs. You would go to a website and then this program would run inside of your browser. And they were this sort of last internet iteration of programs that run on the client side. There were a bunch of issues with Java applets, though. So one of the big ones was that you had to have the correct version of Java installed. So you could go to try to play your little stupid Java game, and you get there and they're like, you don't have the right Java installed. And then you have to download the new Java and install it. Maybe you have to restart your computer and all of that stuff. But in addition to that as a problem, one of the biggest issues you had is that it was essentially downloading a program to your computer, which then had access to all of the resources that any other program had access to. And these applets could be used in effect to take over computers. And in large part due to these security concerns, Java applets have been phased out across the internet. Now, WASM, on the other hand, deals with many of these concerns. And one of the main ways that it ameliorates the security concerns is that it relies on JavaScript's document object model. So a document object model is a representation of resources that are available to the website, both values we care about, like for instance, where we're drawing information from, and ways to get things done, like functions. And the document object model is a primary way that attackers can insert malicious code into a program. JavaScript, as one of the backbones of the internet, has had extensive investments into the security of its document object model. And this helps prevent the injection of malicious code using, if we were just using a new technology like WebAssembly, we might be like, oh, there's not much security built in to prevent the injection of code. But actually, since WebAssembly has handed off its security to JavaScript, we get to leverage all of the decades of work that has gone into that. But that also causes some complications since using WebAssembly requires interfacing with JavaScript's document object model and being restricted by it as well. It's not the nicest thing in the world. But another way that WASM ensures security is that it doesn't provide its programs any knowledge of the browser's resources. And this means that the programs can't know how much memory the browsers have, how many cores it has access to, or anything like that. And when a program asks for resources that aren't provided by the browser, the program just fails. And that makes it secure, of course, but it adds a layer of complication and difficulty to make sure that all users can interact with the software. Another feature of WebAssembly is that it can have what is called symbolic execution applied to it. So symbolic execution is a way of testing the security of a program. So your program has many different functions with many different arguments, and those arguments could lead to different branches on a tree. And symbolic execution means that instead of providing specific values to every argument in every function in order to test out all of the branches of the tree, you just write a program that iterates over arguments and provides them according to a specified formula. So this allows the engineer or the analyst or the scientist to figure out all the values that might trigger certain behaviors and then block paths that are unsafe. But despite these good aspects of security, WASM suffers from some security risks as well. WebAssembly ultimately is executing compiled code. So when code that is being executed can be read by humans, it's easier to see if there's something dangerous or malicious inside of that code. But since WASM's code is compiled, it can be easy to hide malware in the code, which could then end up on someone's computer and doing some bad things. Now, the main mitigating factor against that is that the WASM still has to go through JavaScript security. And so that malicious code would still need to pass through all of those checkpoints. So less extreme than that, but much more prevalent, is that WebAssembly can be used to secretly execute code. So for example, let's think of a benign use case for secretly executing code. Let's imagine that a company is considering using WebAssembly to deliver the next version of its app. When you visit their website, they could run a little WebAssembly program that effectively only tells the company if the browser request would have supported WebAssembly. Like, hey, could this work if I would have asked this computer to do it? And that's a relatively benign use of such a secret execution of code. But there are more malicious programs that could be used. So cryptojacking is when a malicious actor hijacks the client's resources in order to do crypto mining. And this was a large concern when WebAssembly first gained widespread adoption. And indeed, it was actually a problem. So in 2019, it was found that 1 in 600 websites on the Alexa top 1 million sites used WebAssembly. So 1 in 600 out of a million. And 50% of those websites were using WebAssembly to do cryptojacking. So people were visiting them to look at, I don't know, who they should pick for their fantasy baseball team next week. And the computer in the background was like, let me find the number to make money. And so that was, but the thing is, it must not have been very profitable because that number has plummeted. Just in the space of 2 years, by 2021, the percent of websites from Alexa's top 1 million that used WebAssembly that were doing cryptojacking fell to 1%. So it was 50% of websites that were using WebAssembly down to 1%, that were doing cryptojacking down to 1%. So yeah, it must not have been very profitable. You can't, I doubt you, I bet it's a lot of like failed starts, right? Someone goes to a website and clicks back 3 seconds later, and what have you learned in that process? Nothing. But that's only one example of a malicious use of WebAssembly. And the occurrence of these malicious actions shows that WebAssembly security continues to be a moving target, even though WebAssembly is generally seen as safe, generally regarded as safe. An emphasis on security drives some of these, but there are also challenges to using WebAssembly. So one of the biggest challenges we faced as a group while developing our app that you saw a couple weeks ago was getting data into WebAssembly. So it's not trivial, especially if you don't already develop in JavaScript. But there are a couple main options that are too detailed for this presentation, but just for keywords, they include using an mscripten file system image or using indexed DB. So the most important thing to note is that when you're thinking about input and output in a WebAssembly project, if you are not already very well versed in JavaScript, then it will take real design work to figure input output out. Oh, I didn't make my slides nice on this one. Okay, so JavaScript is inherently a single-threaded language that works in a limited environment. But the JavaScript community has, over time, added what are called workers, which allow for multi-threading, and service workers, which allow for proxy network access, so accessing the internet. And when you have a WebAssembly project, both of these types of workers have to be included and managed in order to have a successful application. So JavaScript is currently only 32-bit, which means that WebAssembly is currently only 32-bit, which means that the browser is limited to a maximum of 4 gigs of RAM, which means you can't do any computations that require more than 4 gigabytes of memory. Now that's the theoretical max. The operational max is lower than that in almost all use cases because not all resources are being devoted to the browser. But thankfully, 64-bit is instead, so we should see a lessening of that restriction eventually. A thing to note about JavaScript is that it's a synchronous language, which means that it evaluates all expressions at once, which allows it to deliver a seamless web page. You don't watch like the web page load from top to bottom. Everything sort of happens at once. But it means that anything that requires additional computation has to be told to wait. It has to have an asynchronous operation. And there's this mechanism in JavaScript that allows us to do it, but we have to be conscientious of including it when we're developing projects like this. And then a larger challenge is that not all things can be compiled to run in WebAssembly. And specifically, the libraries and packages that will suffer are those that break JavaScript's document object model, or those that try to communicate natively with the internet. So if you have a package that you like to use that routinely pulls something from a networked resource, like it looks for the most recent census data every time you load the package, then that's not going to be able to be compiled into WebAssembly. WebAssembly doesn't accept curl commands. It can't compile those, in case that's meaningful. So in order for a WebAssembly function to communicate with the internet, it needs to use the mechanisms provided by JavaScript. So now that we've talked about WebAssembly theoretically and seen a few examples of things that might use it, let's look at a toy implementation of WebAssembly. So have at it, Daniel.
Okay, we'll try to go through it quickly then. So you've gotten a lot of information about what WebAssembly is, what it can and can't do. I want to take you through how we can implement a really simple project using WebAssembly. I'm going to show you a little bit of code in this section, but don't worry too much about it, about following through the details. There's going to be a repo attached, actually, if you want to go through this in detail. I'm more interested in highlighting the major components of what WebAssembly, in this case, WebAR specifically, program would look like and how they connect to each other, so that if you're interested in adding this to your toolbox, you can pick it up and work from here. So I'm going to do this by working backwards, first showing you what our WebAR UI is going to look like, and then telling you how to get there. On your screen is a really simple program in R. We're taking the mean and the standard deviation. The user is going to give 2 parameters, and we're going to sample 10 times from a normal distribution and print it out on the browser. This is what it would look like. So the user selects a mean of 50, standard deviation of 5, and we're just going to sample 10 observations for the user. How would you build this? To create a program like this, you need 3 files, or if you want nice CSS formatting like I just showed you, and you need them talking to each other in a single directory. If you're familiar with web development, this is going to be super simple. If you're a data scientist like me, you can get up to speed with the JavaScript and the HTML you need with basic docs. So what are each of these 3 things going to do? The HTML file is just going to give the website basic structure and content. It's going to tell us where our buttons are going, what they're going to say. The JavaScript file sits between the HTML and the R script that runs. It's going to import WebAR, trigger the R function when a button is clicked. And then the R script is actually what's going to run, triggered by the JavaScript. It's going to compute these random samples. It's going to return them to JavaScript and enable that output to be displayed in the browser. This code just tells the browser to show those two fields for user input, and what we saw on the first slide. When that button is clicked on lines 20 and 21, it's going to trigger a JavaScript function that I'm going to show you on the next slide, and it's going to display the output. This JavaScript function, this is a little bit more code, but what it's actually doing is very simple. At the top, it's just importing WebR and getting it set up. Once this code runs, we can execute any R code in the browser. Inside the function call, if you take a look at line 13, we are, and 17, we read in the R script and then we run it. Once we call the function at line 20, that's actually taking the user inputted standard deviation and mean, sampling from it, and outputting to the browser. The other stuff around it is basically just housekeeping, parsing inputs and outputs so that the R code can make sense of it. It's not essential to understanding how the program runs. If you're interested in the details, you can check out either one of these repos. On the left-hand side, you'll see this basic Hello World example. On the right-hand side, you can see a completed project that we talked to you a couple of weeks ago that shows a little bit more fleshed out detail what you can build with this.
All right, thank you all.